This is the review for College Algebra Chapter 4, and there are 21 problems. And the first one is just a calculator, 3 to the negative 2.7, so 3 to the negative 2.7, rounded to 3 decimal places is approximately 0.0515. No work needs to be shown on that, it's just a calculator exercise. Looking at number 2, the graph of an exponential function is given. Select the function for the graph from the functions listed. There's a couple different ways you can tackle this problem. You have all 4 of your options here. You can put all 4 of them into your graphing calculator and see which one matches. I've done a couple things here. I did notice that my graph is going through 1.1. So what I did was I plugged 1 in for the x in all 4 of my options to find out what y goes along with that. And that ruled out C and D, because when I plugged in 1 I got 3, and when I plugged in 1 on D I got 2. So I know it can't be C or D. So now I've eliminated half my possibilities. You can also work on your transformations. You'll see I have some verbiage written down here below. 2 to the x is definitely the parent function. B and C are very similar, whereas they're both vertical translations. The +1 shifts up 1, and the vertical shift down 1 on option B. And I don't think that's happening on either one of these. My asymptote is definitely my x-axis. So if there was a vertical shift, that would have also shifted my asymptote. So I chose A. And you could always double check that by putting it in your calculator. Number 3 is another calculator exercise. No work needs to be shown here. So I'm just going to put in e to the negative 1.7. So you have 2 options. You can do second and your natural log key, and then just put in your negative 1.7 and hit enter and get negative 0.183. It's a positive, not a negative. Or you also have the E option that's on your division key. So either one will work. Number 4. Use the compound interest formula and the continuous interest formula to solve. Find the accumulated value of an investment of 1,000 years at 4% compounded annually for 19 years. So I have to use my compound interest formula, so the first one. So I've plugged all of my information in. My principal is 1,000. My rate is 4%, so 0.04, compounded annually, so my n is 1. I also have my n and my exponent times 19 years. Then when I put it in my calculator, I usually just put in what's in parentheses first, 1.04 to the 19th. And that gives me a decimal, and then I take that times my principal, which gives me $2,106.85. Number 5, I actually have to solve it 2 different ways because they want me to compare. So I have it plugged into my P equals PERT formula and my compound interest formula. So when I plug everything in here and I number crunch, I get 16,792.13 cents. And when it's compounded twice at the higher interest rate, I get $16,721.18. So it's better to invest the $7,000 at 8.75% compounded continuously. You get a little bit more money. Number 6, no work. We're just doing a rewrite. So we're converting from exponential form to log form. So when I do that, I'm using property 1 on your formula sheet. So 7 to the 2nd equals x. The 7's my base. So I have log base 7. My argument is x, and my exponent is always what it's equal to. Nothing else needs to be done on that. Number 7, I used property number 1 again. I took my log, problem, I put equals x behind it just so that I could have it in the form of an equation, so it was easier for me to convert into exponential form. And I took my base of 9, or 9 to the x, equals the argument 1 divided by square root of 9. And now I just convert it to where I have the same base. So my 9 to the x stays on the left. My 1 over the square root of 9, remember square root also means 1/2. And I know that you could have evaluated that and got 3, but then we would have to have adjusted our base on the left side. So we could have done it that way. It'd look a little bit different. But just doing it this way, 9 to the half, and then since it's in the denominator of a fraction, to make it just a regular 9 instead of in a denominator, then it becomes 9 to the negative half. Now that my bases are the same, 9 to the x, 9 to the negative 1/2, I know that x must equal negative half. And again, you could have used that using a base of 3 instead of a base of 9. The process would look a little bit different. So number 8. The graph of a log function is given. Select the function for the graph from its options. I did pretty much the same process I did before. I noticed that 1, 0 is on the graph, and instead of looking at shifts, all I did was I put each one of these into my graphing calculator, and I pulled up the table, or you can evaluate, but I plugged 1 into all of them, and I know that 1, 0 has to be on my graph, so that eliminated option C, because when you plug in 1, you actually get an error. And then it eliminated option B, because when you plug in 1, you get 1. So I know it's either A or D, and the difference is the negative in front. So I went with option D, because a typical log function would actually go up and then level off, and this looks like a reflection. So I chose option D for that reflection. And again, you could put all 4 in your grapher and just compare. Number 9, find the domain. All you do is set your domain greater than 0 and solve. So I got x is greater than negative 9, and I wrote it in interval notation. So greater than negative 9, so negative 9 all the way to infinity would be my solutions. Number 10, I used a couple of properties. I used property 7 and property 1. So the first property I used was property 7, and that's where I have a single log, and I split it into both. It said expand, so that was my clue on that. So I have log base 5 of 125, and I have log base 5 of x, and it's plus because it's a multiplication in here. And then I evaluated log 5 of 125, because as you can see my work down here below, log 5, 125, I put equals question mark, which if I transfer that into exponential form, 5 to what power is 125, and it's 5 to the third. So I'm able to evaluate log 5, 125, or if you've got that option in your calculator and you can put that in, log 5, 125, or you could even use the change of base theorem to figure out 3 if you did not want to go this route. So 3 plus log 5x would be my final expanded answer. Number 11, same type of problem, just instead of using the product rule, I use the quotient rule. Process is the same. The only difference is we have a subtraction here instead of an addition. Number 12, I like to always convert things if I see a natural log into log base e, because I really like to see what that base is. I don't like for it to be empty. So natural log is the same as log base e, and then the square root of 6, or I'm sorry, the sixth root of x is the same thing as x to the 1/6. So I used a couple properties here. I used property number 10, and I used property number 6. So then, because I have this exponent here, I can drop it in front, and that's what I did here, 1/6 log base e x, and that's the same thing as 1/6 of natural log x, and I converted it back to natural log because log base e. Both of these are equivalent. One's just using the natural log, one is using log base e. Same thing. 13, use common logarithms or natural logarithms in a calculator to evaluate. So if you have the option in your calculator to put in multiple or different bases, then you can use that. I did change of base theorem here. So I did log of 13 divided by log of pi, and got approximately 2.2407. But again, if you have that option in your math menu, then you don't have to do the change of base. Number 14. Looks kind of strange the way it's written, so I kind of just rewrote it right here. That x minus 10 divided by 6 is actually an exponent on my base of 4. And then I have 4 here, and I wrote it as base of 4 to the 1/2 instead of the square root. And then because my bases are the same, I was able to set them equal to one another right here. And then I did cross products, multiplied, and evaluated, and got x equals 13. Number 15. Solve the exponential equation. Express the solution set in terms of natural logs. I had a base of e. Whenever you have a base of e, you should always think natural log. And so that's what I'm going to use to solve, because that's my base. The natural log of e to the x plus 8 and the natural log of 4, I'm taking the natural log of both sides. So when I have the natural log, and I didn't write the property down, but when you have, this would be log base e and your argument is e. So when your log and your base are the same as your argument, I have a base of e and I have an argument of e, then those cancel each other out and you're left with just x plus 8 equals natural log of 4. Subtract 8, and my answer is just natural log of 4 minus 8. We could evaluate that in our calculator if they wanted us to approximate, but they did say express the solution set in terms of natural logs, so I'm just going to leave it natural log of 4 minus 8. Don't subtract 4 minus 8 because that's not 4, that's the natural log of 4, so that is a different number. 16. I used property 1. I converted it from logarithm form to exponential form. So my base is 5, my exponent's 3, so 5 to the third equals my argument of x plus 2. And then I just solved. 17, I have property 10 and property 1. So again, because it was natural log, I just rewrote it with log base e, just for me. And that's the only thing I did in this step. And then I took that logarithm form and I wrote it in exponential form. So my base of e, my exponent's 9, so that's where I got e to the 9th, equals the square root of x plus 6. And then to get rid of that square root, I squared both sides. So I got e to the 18th equals x plus 6. And then I just subtracted 6 from both sides and got x equals e to the 18th minus 6. And again, it says give the exact answer, so I left it e to the 18th minus 6, because if you put that in your calculator, you're going to get a long decimal and you'd have to round. So this is my exact answer. Number 18. Since I had logs on both sides, I wanted to get them both on the same side. So I subtracted log 144 from both sides, and I got 2 log x minus log 144 equals 0. You see I can kind of penciled in my 10, because remember, if it just says log and there's no base, you assume base 10. So I just kind of did that as a visual cue for myself. Since it's a subtraction, then I know that I can rewrite it eventually using the quotient rule. But before I did that, because I had this 2 sitting in front, I know that I can put it back and it can become the exponent here on my first term. So I have log x squared minus log 144. Now I can combine it into 1. I have log of x squared over 144. Now I converted that from logarithm form to exponential form. My base of 10, my exponent 0. So 10 to the 0 equals my argument, x squared over 144. Anything that is 0 power is 1. 1 equals x squared over 144. Multiply both sides by 144. I get x squared equals 144. Square root both sides, and I get technically positive and negative 12, but because we're dealing with logarithms, we have to stay positive. So x equals 12. 19. Cindy will require $17,000 in 4 years to return to college to get an MBA degree. How much money should she ask her parents for now so that if she invested at 9% compounded continuously, she will have enough for school? Round your answer to the nearest dollar. So since it's continuously, I use the RT formula. 17,000 is what we want to have, so that's our future amount, so that replaces my A. My principal is what I'm being asked to find, because that's how much she's going to ask her parents for, so that's the big question. Remember, E is a number, so it stays. My rate is 9%, so 0.09, and it's for 4 years. So when I number crunch, I get 17,000 equals PE to the